things happen. So it's a part of monitoring system in ECU, and it monitors the process execution within the CPU, the central processing unit. Why? Because we have a critical real-time system, and a scheduler in the CPU could make errors. So the aim of the PLC is to be able to detect any scheduling error during the scheduling of processes. For example, process inversion, priority problems, deadline, after its deadline, this is not permitted in such systems. That's why we use PLC inside monitoring. Okay. So now we go to the requirements. The requirements of the version, then the current version. So the requirements of the new version is, first of all, that the PLC must support all the tasks that have to be monitored. The current version supports only one task, which is the 10 millisecond task. The second requirement would be that the PLC has to be generic and independent from the number of the tasks to monitor. For example, when we would like to monitor 4 tasks, or 10 tasks, or 12 tasks, this version should be independent from the number of tasks. Then the PLC should have a task deadline detection feature in order to detect task deadline monitoring, like I explained the error about task deadlines. Then the PLC also must have an automated initial parameter generation tool, and this tool would generate automatically some parameters which are necessary for the PLC to execute inside. So now we go to the current version. Brief explanation for the current version. In fact, like I said, the PLC monitors only the 10 millisecond rasta or task, and inside the task we have many processes. And in order to monitor the order and the execution of those processes, we have special treatment which takes place at the beginning of every process. This special treatment would generate a result called a checkboard, and this checkboard would be used in the treatment which takes place at the end of each process. And as a result of this treatment, we have what we call a checksum. And this checksum, after those successive treatments, we have the final version of the checksum at the final process, and this final checksum is a constant known value if the processes are executed at the right order and with the right number. This final checksum is sent to another circuit here. This circuit is called watchdog, and it contains a monitoring module, and this monitoring module takes care of verifying the correctness and the validity of this final checksum sent to the watchdog. And this is performed through a query response communication. The query is sent after every 40 milliseconds, and this watchdog expects an answer shortly after this query. And this answer should be correct, otherwise there is an error counter which is incremented each time we have an error, wrong checksum or wrong path response. And of course, this error counter decreases if it receives the correct value after wrong one. This is, in general, how the current version works. But the thing here is only the 10 millisecond raster or task is monitored, and for monitoring purposes, we have up to 12 tasks to monitor. So now we go to the design of the new version. In fact, the first modification would be to extend the process ID. We have an ID for each process, which was before 124 bits. This process ID has been expanded to 32 bits, and we added 8 extra bits. The first 7 ones are for raster ID, for task ID, because now we have many tasks and we have many processes, and this in order to know which task or process belongs to. This is the aim of the first 7 bits. The last bit is added to be able to detect the last process of the task of the raster, and this is for further treatment that I will explain later. This was about the first modification. The second one is to apply the checksum generation algorithm not only for the 10 millisecond raster as the old version, but for all the rasters that we would like to monitor. This is the execution of the algorithm. We could see here the treatment that takes place at the beginning of every process, and this at the end of every process, and at the end of the last process of each raster, we have a final checksum which will be sent later to the watchdog. And this here we took, we used 2 properties. The first one is synchronization for checksum gathering. This is because we have a scheduler in a real-time system and interruptions could take place. So for example, the checksum generation algorithm would stop at this process, then an interruption comes, then the second task is executed. Then when the algorithm turns back to the first a task, it has to remember at which process it has stopped in order to carry on in the right order. This is about the first property. The second one is state memorizing. I was explaining state memorizing. State memorizing, in fact, we have to save or to remember at which place we have stopped in order to carry on. The second property is synchronization for checks and gathering. Synchronization because we have different rasters or different tasks, and each raster has its own period, its own frequency, and the final checksum is ready at its own period of time. So here we have to take care of when every checksum is ready in order to gather them all together and send them to the monitoring module. This was about the second modification. The third one is to implement test deadline features. In fact, here we divided the tasks into two sets. We have a reference, what we call a reference. This reference tasks in which the checksum gathering takes place. So we have to divide tasks over and below this reference. The first set is about slow tasks, and this set is about tasks that are slower than the reference, which is 10 milliseconds. And the other one is the fast tasks set, and it contains the tasks which are faster than the reference. For example, 2 milliseconds, 1 millisecond, up to 100 microseconds. Here, how we implemented the task deadline monitoring feature. In fact, for slow tasks, we have to wait until the slow tasks here is executed after some number execution of the reference task. Then after that, shortly, we implement what we call verification point, and at this point, we verify that this slow task has been executed at least once during this period. This is how it's made for slow tasks. For fast tasks, it's the other way around. In fact, the first task is executed some number of times, then the reference task is executed. And here, the reference task should make sure that there is the right number of execution of the fast tasks. For example, here, the 2 millisecond tasks should be executed at least 5 times in 10 millisecond period. This is how fast tasks and slow tasks are monitored. In fact, this is not very complicated. It's just about timing synchronization conditions between tasks in order to detect at the right time during which we should make sure that the task is executed. This is about the last modification. Now, we move to some test and validation results. In fact, here I have to explain the test process. In fact, here we use Aspect, which is a tool for integration in order to integrate the monitoring system in the whole system of the car. And this Aspect tool generates what we call a hex file. It's an executable file, and it's the global executable file that we will be flashed later. Then we use Inca, which is a measurement tool and flashing tool. And this Inca, we use it 2 times. The first time is to, what we say, calibrate the hex file, because in the laboratory, we have specific systems, we have specific components, and this hex file should have values which are calibrated with the right components of the system. So here we calibrate the hex file with Inca. Then at the same time, we start here the simulator, which is the lake, which is called black car. And with this black car, we configure what we call a hill box. Hill box is an acronym for hardware in loop, and this box contains, in fact, our ECU, our target, and this box allows us to run the hex file in real time and see the results in real time, and also make the tests in real time. So here, after running the hill box, we flash the calibrated hex file with the debugger in the ECU, which is inside the hill box. Then we go back to Inca the second time in order to measure the variables. In fact, we can start an experiment here in which we specify the variables that we would like to see and the tests that we would like to execute. Then here, after using Inca, we extract some measures which could be displayed with this tool called MD8, it's Mobile Data Analyzer. And here, this tool allows us to see the measured variables and in order to see the results of our test. So as a test results, the first one, we made some test cases for fast tasks. We implemented some permanent errors in scheduling. We surrounded the scheduling in fast tasks, and here we detected that the error counter of the watchdog increases because it receives a wrong value after every 40 milliseconds. Until it reaches here the maximum value, which is 7, and then at 7 we execute some safety measurements. So this is the results of fast tasks. For slow tasks, it's a little bit complicated because stop tasks do not take part of monitoring every time, because monitoring takes place, we have to deliver a checksum every 40 milliseconds, and for example, when you have a task, 500 millisecond task, it does not take part of monitoring every time. So here we implement two properties. The first one would be to memorize the state of the error. For example, when an error takes place in a stop task, it has to be memorized because it will be used later. For example, here we see the first error, then here we see the first error and the second error. This means that the first error has been memorized and the second error is also detected. And this just ups and down because the monitoring module takes awareness of the accumulation of the errors in stop tasks until it reaches here the 7, which is the maximum value, and here, like the first test result, we execute some safety measurements. This was about results of testing and validation of the PLC. Now we move to the offline tool to see what it is exactly. The offline tool is about a per script, and it works at 3 steps. In fact, the first step is to gather some information, basic information from tasks. How many tasks you would like to monitor, how many processes inside each task. Those information are set in an XML input file. So the first step is to read and parse this XML and extract the necessary data in order to generate the values that we need. So here, the values calculation takes place, and then the data generation is displayed in what we call output header file. It's a header file which respects the C norms, and this header file will be just copied to our project, to our source code of the system. So let's take a look exactly how it works inside. In fact, the user, which is the developer, this is a developer-oriented script, has just one use case. It's when he would like to generate the parameters, then it has, of course, to execute the script. And then the script take 5 parts. The first one would to read the XML data here. Then those ones is about the parameters generation. Then the second step is to display and generate the header file, which will be copied to our source code. This is how the offline tool works in general. So now we move to a conclusion. In fact, I can say here that the internship objectives are met. In fact, I provided a technical tip documentation for the old version, because here they had the version working, but they didn't have an idea how it worked. Then here I needed to make some reverse engineering in order to understand how the current version works in order to develop the new one. So I provided also an executable, what we call program stand, with the new version of the PLC working properly. The program stand is the source code of the global system in an executable file, and it contains the new version of the PLC, and it's working properly after performing the test cases. I have also provided a user guide and a technical documentation for the new version of the PLC in order to let the developers and the other people understand how it works. I have also provided developer-oriented and documented script as a component of the new PLC. It's about the offline per script. And least but not, at the last part, I provided some test case sheet in which there are all the performance tests and its results and their outputs. Of course, the PLC is subject to improvements following the technology wheel, because systems are becoming more and more complicated, and this, monitoring is a very important part in such critical systems. So monitoring has to follow the complication of the system. So this version, of course, is subject to improvement. For example, we could enhance the communication between the system and the watchdog, because like I said, this communication is every 40 milliseconds. It could be enhanced to, for example, 20 or 10 milliseconds in order to make the system more stronger, more faster, and in order to make it able to detect errors faster. This was the conclusion of my presentation. So at the end, I would say thanks for your attention and your questions.
Thank you.